Before we apply calculus to a problem, let's take a look at the problem from a slightly different point of view and just try to reason out what's going on. So suppose we want to find two numbers whose product is the maximum possible. So maybe we decide to just organize the information in a table and come up with a couple of numbers that we then find the product for, and try to decide if that product of 50 is the biggest possible. Well, probably not. We could pick a couple of different numbers and the product there is bigger than 50. How about if we try 100 and 500? Well, now our product is 50,000, so that definitely is bigger than the other two numbers. Well, as you can see, we can keep picking numbers and multiplying them together and getting a product, and our product just keeps getting bigger and bigger and bigger. So we can't exactly find a maximum product here. We've got to have some sort of constraints on these two numbers that we're picking. Otherwise, the product is just going to keep getting larger and larger. So what if we change the problem a little bit? And we said find two numbers whose sum is 20 and whose product is the maximum possible. Well, now we've got something different to consider. We're still going to look at the product of the two numbers, and we're going to see if we can make that product as big as possible, but we want to make sure that the two numbers that we're choosing add up to 20. So maybe we'd try 1 and 19. Now that adds up to 20, and the product of 1 and 19 is 19. But is that product the biggest possible? Well, maybe we'd pick 5 and 15 for our two numbers. Those add up to 20, and look, we have a bigger product. That's 75. And we could keep doing this and keep looking for a bigger product. 8 and 12 gives us a product of 96. Now, is our product just going to keep getting bigger and bigger? Well, what if we try 14 and 6? Well, now the product's getting smaller again, isn't it? So there must be some set of numbers that we could multiply together and get a biggest product. And we could keep guessing and checking and try to find those numbers, but maybe we can use some methods we learned in calculus, because we know in calculus we can find maximum values with derivatives. So if we're trying to solve a problem where we're maximizing or minimizing something, we're going to look for a constraint on the thing that we're maximizing. So in this case, we're finding two numbers, which maybe we'd call x and y, but the constraint on those two numbers is that the sum of the two numbers has to be 20. So we certainly can say that x plus y has to equal 20 if the sum of the numbers is 20. Now let's think about the thing that we're trying to maximize, which is the product of these two numbers. Well, the product of x and y is x times y. So if that's the thing we're trying to maximize, that's the thing we're going to be taking a derivative of. Now the problem is that expression that we have for the product has two variables in it. And although it is possible to take a derivative of an expression that has more than one variable in it, at this point we don't know how to do that. So let's look back at the constraint that we had, which was x plus y has to equal 20. And let's solve that constraint for one of our variables. So in this case we could say y equals 20 minus x. Now remember, y was the second number. So we now have a different expression that means the same thing as y, which is 20 minus x. So the second number, 20 minus x, can replace the y in our expression for the product. So now we can say that the product is x times 20 minus x. And since that expression has only one variable in it, we can say that that is the function which describes the product of the two numbers. Now we're trying to maximize that product, so since we want to maximize it, we're going to take a derivative of it. And we might want to rewrite that expression so that we can take the derivative more easily. So if we distribute the x, we'll have 20x minus x squared as an expression that still means the product of the two numbers. Now if we take the derivative of that, we get 20 minus 2x. And we know that if we want to maximize something, we can find critical values by setting it equal to 0 and solving for our x. Now 10 is a critical value for our function, and I'd like you to think about the function and determine whether that critical value does represent a maximum. The function, remember, was 20x minus x squared, and we know that that's a quadratic function, which means it's a parabola, and in this case it opens down because x squared has a negative coefficient. So since this function represents a parabola that opens down, this critical value has to represent a maximum. Now x was the first number. We need both numbers, and the second number is 20 minus x. So the second number has to be 10 as well. So the two numbers are 10 and 10. So what we're saying here is that 10 and 10 both add up to 20, and the product of 10 and 10, which is 100, is the largest possible product for two numbers that add together to give us 20. Here's a graph of the function. Now, just as we expected, it's a parabola that opens down. The horizontal axis represents the value of x, which was our first number, and the vertical axis represents the product of those two numbers. The other thing you can notice is that the vertex is at 10, 100, which is exactly what we expected. We said that the maximum value occurs when our first number is 10, and the product of those two numbers, which were 10 and 10, is 100, which is our maximum value for the product. Here's another problem. A farmer has 500 feet of fence with which to build 4 pens for his 4 sheep. He will build a rectangle out of the fencing and then use fence to make 3 dividers within the rectangle. He wants to maximize the area within the pens, and he also wants each of the 4 pens to have the same area. What dimensions will give the pens the maximum area? What will be the total area of all his pens? Well, let's think about what this would look like. He's got these 4 sheep, and he's going to build a rectangle out of this fencing. But he's also going to put dividers between all of his sheep so that he has 4 pens for his 4 sheep. Now what we want to do is maximize the total area. So we're going to have to figure out a way to write an expression for the total area of all the pens. So let's label some of the sides here. Let's say that this side, which is the length of the 2 sides on the left and the right and each of those dividers, is x. And let's say this side is y. Now because we have a rectangle, we know that the side opposite the one we just labeled y is also y feet long. And we know that each of these dividers, as well as the right side, have to be x feet long. Now remember, there's always going to be a constraint in each of these problems. And in this case, the constraint is coming from the fact that he only has 500 feet of fence. So if we look at how that fence is split up to make each of these sides and the dividers, you'll see that there are 5 lengths that are x feet long and 2 lengths that are y feet long. So 5x plus 2y has to equal 500. Now the thing we want to maximize is the area. And the area of the entire enclosure is x times y. Now once again, we've got something that we're going to be taking a derivative of, our area function, but it has two variables in it. So what we'll have to do is go back to our equation that talked about the constraint, which was the limit on the fencing we had, and we'll have to solve it for one of our variables. Now it doesn't matter whether we solve it for the x or we solve it for the y, as long as we solve it for one of the variables, so that we can substitute that into our area equation. Now that gives us a function that describes the area of the entire rectangle. Since we're going to have to maximize that area, we will be taking a derivative. But before we take the derivative, we might want to go ahead and distribute the x to make the derivative a little easier to take. If we don't do that, then we're going to have to use a product rule to take the derivative, and that's a little bit messier. So now we can take the derivative of our area function, and since we want to maximize it, we'll set it equal to 0 and find our critical value, which is 50. Now before we go on, think about that area function we had. F of x equals 250x minus 5x squared. That's a quadratic function again, which means it represents a parabola that opens down. So this critical value has to be a maximum for this function. This is what our pens look like. And we just found the length of all those pieces that are a length of x feet. We still need to find the lengths of the two sides that measure y feet. So we'll use this equation that relates x and y and just substitute the 50 in for the x. So we can see that the length of y has to be 125.5 feet. And that lets us answer the two questions we had in the problem. What dimensions will give the pens the maximum area? Well, that's 50 feet by 125.5 feet. And then what will be the total area of all the pens? Well, that's 50 times 125.5, or 627.5 square feet. Here's another maximization problem. A souvenir shop has determined that 60 mugs can be sold each week if the price per mug is $10. For each $1 increase in price, 4 fewer mugs are sold. What price should be charged to maximize the income earned from mug sales? Now, the thing we're trying to maximize in this case is the income. So we'll think about how the income is earned. The total income is the number of mugs sold times the price per mug. Currently, 60 mugs are being sold at $10 per mug. So right now the income is 60 times 10, or $600 a week. Now the variable in a problem is the thing that is going to change. And in this case, what's going to change is the price that's being charged for a mug. So since we're changing the price in $1 increments, we'll let x be the number of $1 increases in price. How does the income change if we change the price by a certain number of $1 increases? Well, we're starting by selling 60 mugs, but every time we increase the price by $1, we're going to lose 4 mugs in sales. So we're going to have 60 minus 4 times x, where x represents the number of $1 increases. Stop and think about why that works. Let's say we had one $1 increase, so we're now charging $11 for a mug. We're going to lose 4 mug sales. So 60 minus 4 times 1 means we'd only sell 56 mugs. What if we have 2 $1 increases? In other words, we're now charging $12 for a mug. Then we would lose 2 of those 4 fewer mug sales, and 2 times 4 is 8, so now we'd be down to 52 mugs sold. Now how about the price per mug? Well, the price per mug starts at $10, but then we're increasing it by X dollars. So we can say that the expression for the price per mug in the future is 10 plus X. If we multiply those together, we get that income in the future. And we certainly could do that multiplication to give us a quadratic function that's going to be a little easier to work with. Now, the reason why that's important is that we know we're going to maximize the income, so we will be taking the derivative of that income function. The derivative of that income function is negative 8x plus 20, which we know we need to set equal to 0 to find our critical value. Now our critical value is 2.5, and remember, x represented the number of $1 increases. So 2.5 increases of $1 means we'd be increasing the price by $2.50. So the new price is $10 plus that increase in price, which is $12.50. How many mugs would we sell then? Well, remember, x is 2.5, and the number of mugs was 60, that original amount, minus 4 times 2.5. Remember, we lost 4 mug sales for every $1 increase in price. So we're going to lose 4 times 2.5 because we've increased the price by 2.5 $1 increases. So we're going to sell 50 mugs. And how much income will we get? Well, 50 mugs that are sold at $12.50 would mean we have an income of $625. Here's what a graph of that function would look like. Remember, x represented the number of $1 increases, and the y-axis is the income. So the vertex of this parabola is at 2.5, 625, meaning 2.5 $1 increases, which is $2.50 increase in the price of a mug, will result in a $625 income. Now, for all the problems we've looked at so far, we had to write a function for something that we were trying to maximize or minimize, and we had to use a constraint in order to write that function with only one variable. This is a slightly different problem. We aren't going to have to write a function the way we did before, writing a function completely from the beginning, and we aren't going to have to consider a constraint. So here we go. A stereo manufacturer determines that in order to sell X units of a new stereo, the price per unit in dollars must be P of X equals 1,000 minus X. The manufacturer also determines that the total cost of producing X units is given by C of X equals 3,000 plus 2X. We're going to find the total revenue, find the total profit, figure out how many units the company has to produce and sell in order to maximize the profit, find the maximum profit, and then find what price per unit has to be charged in order to make that maximum profit. So let's start with find the total revenue. Now we've been given these two pieces of information. We have a price function and we have a cost function. Revenue is how much money we can earn if we take the quantity times the price. In other words, how many did we sell times the amount that we sold them for. That's exactly what we did in the mug problem, where we had to write a function for the amount of income that we would get from selling mugs. In this case, the quantity that we're selling is X, and that's given in the problem. It says the stereo manufacturer determines that in order to sell X units, and the price is given in the price function. So the revenue we can find by taking the quantity X times our price function 1000 minus X, which is 1000X minus X squared. So we'll add that revenue function to our list and now find the total profit. Now profit is total revenue minus total cost. It's how much money we get paid when we sell the item minus how much it costs to manufacture the item. We do have a revenue function and we do have a cost function. So if we subtract the two, we'll have a profit function of negative x squared plus 980x minus 3000. We'll add that to our list so that we can go to our next question. How many units must the company produce and sell in order to maximize profit? So now we see that word maximize, which tells us that a derivative would help us find a maximum value. Since we're trying to maximize profit, we're going to have to take the derivative of our profit function, which is negative 2x plus 980. And we'll set that equal to 0 to find our critical value, which is 490. Now, since our profit function is quadratic, we know that we have a parabola, and we know that that parabola opens down because the coefficient of the x squared term in our profit function was negative. So that tells us that this critical value definitely is a maximum. So since X represented the number of stereos that this manufacturer made and sold, we can say that the profit is maximized when 490 units are bought and sold. So what is the maximum profit? Well, we know that we have to sell 490 units to make that maximum profit. So we'll look at our profit function and find the value of the profit function at 490, which is $237,100. So the manufacturer will make the largest profit of $237,100 when 490 units are bought and sold. What price per unit must be charged in order to make this maximum profit? Since 490 units have to be made to maximize the profit, we'll use 490 in our price function to find that the price that should be charged for the stereos is $510. That will give us the maximum profit. So let's turn from looking at maximization problems to looking at another business application, which is something called marginals. So let's suppose that a manufacturer produces and sells X items. And we have a cost function that represents the total cost of producing all X of those items. And we have a revenue function that tells us the total revenue from selling all X of the items. How can we find the profit, P of X, of selling all X items? Well, we've already said that profit is revenue minus cost. So if we simply subtract our cost function from our revenue function, we'll have a profit function, which, remember, tells us the total profit of selling all X items. So now that we've got this profit function, can we find the total cost, the total revenue, and the total profit from producing and selling 50 items? Well, certainly, all we have to do is substitute 50 in each of our functions. So the total cost of producing 50 items is C of 50, which is $182,500. The total revenue of selling all 50 items is R of 50, which is $97,010. And the total profit from selling 50 items is P of 50, which is negative $85,490. Now, if that negative bothers you, think about the numbers that we have for total cost and total revenue. If it costs $182,000 to make something, but the revenue you get for selling it is only $97,000, you're going to lose money. So that's why we see a negative value for our profit. So we know that C of X is the total cost of producing X items. And we've already said the total cost of producing 50 items is $182,500. What's the cost of producing 51 items? Well, we can still use our cost function because it still gives the total cost, but this time of producing 51 items. So 51 items will cost $188,762. Now, how can we use those two pieces of information to find the cost of producing just the 51st item? Well, if we know the cost of producing items 1 through 51, and we know the cost of producing items 1 through 50, all we have to do is subtract the cost of producing 51 items minus the cost of producing 50 items. Now that $6,262 is the exact cost of producing item number 51. Now we've said that the manufacturer produces and sells X items, which means the item after item X would be item X plus 1, the X plus 1th item. So the item after the 30th item is the 31st item, or the item after the 70th item is the 71st item. Now if we know the cost of producing a total of X items, then we can come up with an approximation of producing the next item, item X plus 1, by using a derivative. And that derivative is something that we call the marginal cost of producing that X plus first item. So if we wanted to approximate the cost of the 51st item for this function, we would find the derivative of the cost function, and then we would approximate the cost of the 51st item by evaluating that derivative at 50. And we would find that the approximate cost of the 51st item is $6,200. We call that the marginal cost when 50 units are produced. That means the approximate cost of the item after the 50th item is produced. As you can see, that's really close to what we came up with for the exact cost of the 51st item. But because we found the marginal cost by using a derivative, we have an approximation for the cost of the 51st item. Now this also can be used to find what's called marginal revenue, which is the approximate revenue from selling the next item after the first X items are sold. So if we have a revenue function and we take its derivative, we'll have a marginal revenue function. So if we want to find the approximate revenue for selling the 51st item, we'll find the value of our derivative of our revenue function when X is 50. So the marginal revenue when 50 units are sold, which really means the approximate revenue that we get for selling the 51st item, is $6,340. And similarly, we can find the marginal profit, which is the approximate profit from selling that next item after the xth item, and we can find that by taking the derivative of the profit function. So this was our profit function, and this is its derivative. If we want to know the approximate profit from selling the 51st item, we can find the value of the derivative at x equals 50. So the marginal profit when 50 units are produced and sold is $140, which means we will get an approximate profit of $140 for selling the 51st item.